All right, welcome everybody. Today we're going to talk about section 5.3, day 1, and this is all about graphing radical functions. In sections 5.1 and 5.2, we've done a lot of work with calculating square roots and cube roots and fourth roots, and now we're going to talk about what the graphs of those functions would look like. We're going to focus mainly on the square root on the left, which is of course index of 2, and then the cube root over on the right, which has an index of 3. Keep in mind that any radical with an even index, so to the second, fourth, sixth root, they're all going to look similar to the square root function, whereas any function with an odd index, so a cube root, a fifth root, a seventh root, they're all going to look similar to the cube root function. So hopefully if we just focus on these two, we'll be able to kind of extend upon those for harder examples. So let's go ahead and start by focusing on the square root. You probably have seen the graph before, maybe not lately. So let's go ahead and talk about where it would come from. If you don't know what something is supposed to look like, your first order of business would be perhaps to make a table of values. So let's go ahead and do that. If we were to make a table of values, let's go ahead and say xy. Technically, in this case, it's xf of x, but you get the idea. If you were to think about the smallest possible thing that you could take the square root of, that would actually be 0. The square root of 0 would be 0. Think about why you could not put any negatives into the x column. If you did the square root of -1 or the square root of -2, anything less than 0 would give you an imaginary value, which of course is not graphable, which makes 0, 0, the smallest possible x and the smallest possible y. If you're now going to choose additional x values, my advice would be to choose the nice values of x, meaning the things you know the square root of. So after 0, the next thing I know the square root of is 1, then 4, then 9. Those are, of course, my perfect squares. The square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. I could keep going, but that's really enough for me to get an idea of what the graph is supposed to look like. So here at 0, 0, here at 1, 1, here at 4, 2, and here at 9, 3. When you go to connect those dots, you're going to connect them with a curve, kind of looks like a scoop, and you should go ahead and have an arrow on the right hand side. You want to really focus on this point right here, 0, 0. That is the end point. As you go to move this function around, you really want to focus on where that 0, 0 point goes, because if you can follow that point, you can really figure out where any of the points are going. Now we want to talk about domain and range. So again, domains are always x's and ranges are always y's. And we're going to ask you to give those domain and ranges in interval notation, but we'll go ahead and start using inequalities just to make sure that we remember the relationship. So when it comes to the domain, we're talking about the x's. If I look at where the first x value of this graph is, it's right here on the y-axis, which means that x has to be to the right of 0, and so x is greater than or equal to 0. When you're talking about interval notation, if you're saying greater than or equal to 0, that means you're going from 0 to infinity, and you're going to include the 0, but remember, never include the infinity. When you're talking about the ranges, you're talking about the smallest y value. So the smallest y value is here on the x-axis. It also has a small y value of 0. So your range is going to be y is greater than or equal to 0. And in interval notation, that would look exactly the same, 0 to infinity. Will these domain and ranges change as you move this graph around? Yes, and they will change in a very particular way. So when you're talking about the domain, this can change when the graph moves left, right, or if there is a reflection over the y-axis. Then when it comes to the range, is the range going to change? Yes, the range will change if you move the graph up, down, or if you reflect it over the x-axis. So if you write those down now, you'll be able to kind of keep them in mind going forward. Again, this table right here, this is a table of the parent functions. We are going to want that a lot more for day 2. But for now, if you ever forget where the graph came from, go ahead and go back to your table there. So just like we made a table of values here for the square root function, we're going to go ahead and make a table of values for the cube root function, but it is going to be a little bit different. Not only are we going to try to choose values that we actually know the cube root of, but remember, because you're taking an odd index, you're allowed to do it not just for positives, but for negatives as well. We're actually, though, going to start with 0 because the cube root of 0 is, in fact, 0. If you think about the positive perfect cubes, the first one that you know is 1, and the second one that you know is 8. The cube root of 1 is 1. The cube root of 8 is 2. Again, in the previous problem, the square root, you were not allowed to take the square root of a negative, but you are allowed to take the cube root of a negative. So why not choose those same perfect cubes, but the negative versions? So the cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1. So again, if you ever forget what the graph looks like, all you have to do is make yourself a little table here. Go ahead and find those x and y coordinates. As you go to connect them, the piece on the right looks similar to the square root. It's actually rising a little bit more slowly, but it still has an arrow off to the right. Then you're going to have a similar looking scenario off there to the left. And just to kind of make that a little bit more perfect, there you go. Graph looks like such, has an arrow now pointing to the left side. And again, even at just a quick glance here, you should understand that because of the fact that you were allowed to include negative x's in your domain is why the graph fills the entire region from left to right, whereas in the previous problem, you only had to start at 0, which is why you only have values on the right-hand side of the graph. So when it comes to domain and range, turns out that this is actually going to be much simpler. The domain and the range is always going to be all real numbers. And of course, in interval notation, you would write all real numbers as negative infinity to infinity, and you're going to always parenthesize those. Here's the even better thing about domain and range is that these never change. And that's true for domain and range. No matter how you move this cube root up or down or reflect it, no matter what you do, you're always, always, always going to have pieces in both directions. So you're always going to have a domain and a range of all real numbers. Just like in the previous problem, 0, 0 was kind of the most important point to follow. That is a similar case here. If you figure out where that 0, 0 moves, it's kind of where the two pieces meet, you'll be able to figure out where the entire graph is moving. So let me just go ahead and kind of show you those two pictures. Again, everything we do for the next couple of days is going to focus on your graph of both the square root and the cube root. So just make sure you're using the left-hand side whenever it's a square root and the right-hand side whenever it's a cube root. So all this talk that I've been saying about moving the graph and reflecting it, that of course brings us back to chapter 1 and all those transformations. We had told you at the time that those transformations would come back again and again, and here they are back in chapter 5. So let's see what the problems underneath are asking us to do. They're asking us to consider the parent functions above. So again, refer to the graphs above if needed. You're going to first describe the transformation of the graph in words. Then you're going to find each graph's equation. And then lastly, you're going to state the domain and range in interval notation. So quite a bit is going on here. Then there's also a bit of a qualifier. Assume that no graph has a stretch or a shrink. When it comes to finding a stretch or a shrink, it's actually pretty hard to do from the graph. It's easier to do from words, which we'll do in a minute. But before we get into that, it would be helpful to refresh ourselves on the transformations. So lucky for you, I have a copy of those on the back side. So let's go ahead and do a quick refresher of those before we go ahead and try the problems. So notice that not only do I have for you here the transformations described in words, then in the middle, I have them given with f of x notation. And then over on the right, these are specific to the square root. You will also want to know that these are the same for the cube root of x. Okay, obviously, instead of having an index of 2, you have to put an index of 3, but all the rules still apply. So let's go ahead and refresh ourselves of these. And again, you can have these in front of you, print them out, write them down. So there really should be no excuse for getting these transformations wrong since everything is open notes. So first, how do you move the graph up or down? Those are your vertical translations. Those happen on the outside of the function, and you're always going to follow the sign. So a positive 3 outside moves it up 3, where a negative 4 on the outside moves it down 4. Whenever you're talking about a vertical translation, just to reiterate, this is a Y change because you're moving up and down. Then you have your horizontal translation. That is what moves the graph left and right. Remember that in order to move the graph left and right, you have to be inside. And whenever you're inside, you, of course, do the opposite. So inside implies you're doing the opposite. And again, just to show you why that is, notice that here inside the first one, you have a -2, but you're going 2 to the right. Whereas in the next one, you have an x plus 1, but you're going 1 unit to the left. So whenever it's inside, you have to do the opposite. And it's worth noting here that these are x changes. Then you have your vertical stretches and compressions. And just so you know, a compression is another word for shrink. We have tended to use the word shrink instead of compression, but please make sure you know they're the same. So when you see the word vertical, hopefully you remember that that means that this is a Y change. And again, those Y changes happen on the outside. So if you wanted to make something larger, you would have a number bigger than 1 outside. So this would be a vertical stretch of 6. If you wanted to make something shorter, you would have something between 0 and 1 outside, and that would give you a vertical shrink or a compression. Then horizontal stretches and shrinks. Again, now we're back to inside. So when it comes to inside changes, remember you're going to do the opposite. And remember that these are x changes. So again, you're thinking here inside opposite. So if you actually want to horizontally stretch something, you would put a fraction inside in order to make it bigger. Whereas if you wanted to shrink something, you would put something inside that was bigger than 1. So anything that's happening to the x is happening on the inside, and it's the opposite. And then finally, you have the two reflections. If you have a negative on the outside, that's the one we've had more practice with. That is going to be a reflection across the x-axis. Whereas if you have something on the inside, that is going to be a reflection across the y-axis. And then just in keeping with what we've done so far, if you're reflecting something across the y-axis, if you're reflecting across the x-axis, that's going to be a y change. Whereas if you're going across the y-axis, that's going to be an x change. I know I might have said it wrong, but I wrote it right. So as you reflect over the x-axis, you're changing the y value. And as you reflect over the y-axis, you're changing the x value. So if at any time you forget about your transformations and you need to see the rules, here they are in black and white and actually in several colors. So help yourself to that. Let's go ahead and take those transformations and then head back to the front side and go ahead and answer what is being asked. So notice that the first two problems are both square root problems. So the best way to start those is to identify that endpoint. If you can identify where that endpoint is, if you go back to the original, if you consider the point 0, 0, if you can follow where that point 0, 0 went, then you can identify the transformation. So here in the first one, it appears as though the endpoint moved 4 to the left. So I'm going to say that the transformation in words is left 4. Over here on the right, I think it's fair to say that this went 1 to the right and up 2. So once you have identified what the transformations are in words, let's go ahead and write an equation. So for now, you can call it y equals or g of x equals or whatever you want. I'll call it y equals. You want to take the square root function and you want to move it left 4. In order to go left and right, it has to be inside the radical. And whenever it's inside, it's the opposite. So in order to go left 4, you would have to have the square root of x plus 4. Here for the second one, again, let's make it a y equals. In order to go right, you have to be inside the function, and it has to be the opposite. So to go right 1, you would need the square root of x minus 1. Then to go up 2, you would need a plus 2 on the outside. Then you need to discuss the domain and the range. So when it comes to the domain, remember that the domain is the x value. So the lowest x value over here would be -4, and then to the right. So how do you say everything greater than or equal to -4? You would start at -4 and then off to infinity. You're always going to bracket your values here for the radicals. So bracket on that -4. Similarly, over here, the smallest x value here is equal to 1. So your domain is going to be bracket 1 to infinity. Then let's go ahead and consider the range. So the range is the y values. So the lowest y value here on the left would be 0. So you can say that the range would be from 0 to infinity. And over here on the right, the smallest y value is 2. So you could say that the range was 2 to infinity. So these problems are really kind of great because they're pulling everything together, not just from here in chapter 5, but from other sections as well. So anything about square roots, refer back to this graph on the left side. Now we're talking about a cube root situation. So we're going to refer to the graph up top on the right-hand side. So again, if you go back to that graph up here, remember 0, 0 is again the most important point. If you can figure out where that 0, 0 is, which is the point that connects the two pieces, that's going to tell you the whole story. So if you try to identify where that point is, here in the left, it appears to be here. And over here on the right, it appears to be here. Again, that special point is always where the two, scoops kind of meet. So if you compare that to the original graph on the top right, I think it would be fair to say that you're going down 2 over here on the left. Whereas over here on the right, I think it's safe to say that you're going right 4. And again, there is no stretching and shrinking. I said that up front, so you don't have to worry about that. So now it's time to write an equation. So if you're going to write an equation, how do you take a cube root and go down 2? Well, first, you have to start off with a cube root. Again, don't forget the little 3. And then to go down 2, it's a big -2. How would you go right 4? Well, you're going to go ahead and again start with a cube root. In order to go right 4, you have to be inside. But remember, it's the opposite. So you're going to put the cube root of x minus 4, and that means 4 to the right. While it can be a little difficult to remember what goes inside and outside, the very good news about anything with a cube root is that when it comes to domain and range, there is absolutely no work required. 100% of the time, it has to be all real numbers. It goes all the way left and all the way right and all the way down and all the way up. And that's going to be true for both of these. So domain and range is all real numbers all of the time. So to finish us up here, we just want to do, again, a little bit more reminders about these transformations, making sure we remember what goes inside, what goes outside. And now that you're doing it in words, here is where I can ask you some more challenging versions. So to bring back those stretches and shrinkings and reflections, since it's a little bit easier to do from words than it would be to do from a picture. So notice everything here on the left side, we're talking about a square root. So every problem that you write should be a square root. They're telling you that that is the parent. So you're going to write all of your equations as a transformation, which is going to be g of x. So you're going to say g of x equals. If you have the square root of x and you now want to move it up 5, you're going to put the plus 5 on the outside. If you want to go left 2, you're going to put inside the opposite, which would be the square root of x plus 2. Here in the next one, no matter what, you know you're starting with the square root of x, and then you want to apply each of the transformations in the order that they're given. So when they say that you want a vertical stretch of 3, if you don't remember what that means, literally go up to the rules here, look for the one that says vertical stretch, and follow the example. So the example there, if you want to vertical stretch it by a number, you should put that number on the outside, which is how I know that I'm going to put a 3 here. Then after you do that, you want to reflect it over the x-axis. So reflecting something over the x-axis, if you forget how to do that, go back up here, locate that transformation. So over the x-axis means you're going to put a negative out front. So that's going to be a -3. So -3 times the square root of x takes care of both of those transformations. And then finally, you want to take your square root function. So again, let me go ahead and start with a fresh copy. If you want to go ahead and vertically shrink it by a half, a vertical shrink happens on the outside and you put exactly what it says. So that's how you know you're going to put a 1/2 out front. Then if you want it to go right 6, remember that has to happen on the inside and it has to be the opposite. So right 6 would be, oops, -6. And again, guys, I mean, all I can do for you is give you a list of the transformations and ask you to look at it. So if you're not willing to do that, I'm not sure how much more I can do for you. And then let's finish up over here. Same exact idea, but now you're doing it for the cube root. So that just means that all your answers should have a cube root in them. So if you want to go 8 to the right, you're going to say g of x equals. You're going to start off with the cube root. And again, to go 8 to the right, it has to happen inside and be the opposite. If you want to go down 6, it has to happen outside and you have to follow the sign. If you want to vertically stretch something by 2, you're going to put the 2 on the outside. And if you want to if you want to reflect something over the y-axis, that means that you have to put a negative inside of the cube. And again, I get that information above. Then finally, you're going to go ahead and again start with a cube root. In order to vertically shrink it by 1/3, that means you're going to put a 1/3 on the outside. And if you want to go left 5, that means that inside of the cube, you're going to have to do the opposite. So to make it go left 5, you're going to do the cube root of x plus 5. So hopefully after today's lesson, you have a good reminder of the transformations, a little bit of a reminder about domain and range, and then of course, what the graphs of the square root and the cube root look like. So we'll do a little bit more detailed problems tomorrow. But for now, thanks for tuning in, guys, and we will catch you next time.